All right, welcome back. So last time, we dug into the theory behind the vector equation of a line. Today, today's all about getting our hands dirty and putting that theory into practice. We're going to tackle 3 classic 3D problems, and then, just to make sure it all sticks, we'll finish up with a quick exam drill. Ready? Let's jump in. So here's the game plan. First, a super quick look back at the core formula. It's going to be our best friend today. Then we'll dive into 3 pretty cool 3D problems. One about crossing planes, another about lines and angles, and a trickier one on finding perpendiculars. And to wrap it all up, a quick exam question drill. Sound good?
Okay, first things first. Let's do a quick but absolutely crucial refresher. I'm telling you, everything we're about to do hinges on this one formula. So let's make sure we're all on the same page.
So let's just pause for a second and ask, what is this thing really? The vector equation of a line. I mean, it's more than just a bunch of letters and symbols on a page, right? You can think of it like a set of instructions for a journey.
And here it is. It's actually pretty intuitive. To get to any point R on a line, you've got to do 2 things. First, you need to actually get on the line. That's what vector A does. It's your on-ramp, taking you from the origin to some known spot on the line. Then, once you're on it, you just travel along it. That's your direction vector D. The T is just a scalar, a number that tells you how far to go in that direction. You can go forward, backward, a little, a lot, whatever. So A gets you there, and T times D moves you around. Pretty simple when you think about it that way.
All right, enough theory. Let's dive into our first real problem. We're going to use this equation to figure out something pretty cool. The exact point where a line in 3D space literally punches right through a flat plane.
Okay, so we're jumping into exercise 9D from the textbook. We're going to hit questions 5, 6, and 8. First up, number 5. So this one's got 2 parts. The first part's pretty standard. Just find the equation of the line that goes through points A and B. But then for part 2, we need to find the exact coordinates where that line crosses the oxyplane. Let's break it down. Okay, step 1 is always getting our direction vector D. Easy enough. We just subtract A from B, which gives us 1, -3, 8. Now we need a point to start from, so let's just use point A for our position vector A. Put them together and boom, there's our full vector equation. From here, pulling out the parametric equations is a piece of cake. You just look at the x, y, and z components one by one. Now here's the key bit of logic. What is the oxyplane? Well, it's just the flat surface where z equals 0. So if our line is going to cross that plane, then at that exact point of crossing, its z-coordinate has to be 0. See where this is going? We just take our z equation, set it to 0, and solve for t. That value of t is like our magic key. It tells us the precise moment or distance along the line where we hit that plane. So we just take that t value, which is 1/4, and plug it back into our equations for x and y to get the final coordinates. And there we go. That's the exact point of intersection. Problem 1, done and dusted.
All right, let's level up. For our next problem, we're moving on from a line and a plane. Now we've got 2 separate lines floating around in 3D space. Our job? Figure out how they relate to each other and, specifically, find the angle between them.
Yep, another 2-parter. First, we've got to show they're not parallel. Pretty straightforward check. And then, once we've done that, we need to calculate the actual angle between them. You know, the test for parallel lines is actually super simple. Think about it. If 2 lines are parallel, their direction vectors have to be pointing in the same direction, right? Or the exact opposite. That just means one vector has to be a multiple of the other. So we just check the ratios of the components. Is 6 a multiple of 1? Yeah, by 6. Is 1 a multiple of 1? By 1. Uh-oh. Since those multipliers aren't the same, there's no way they're parallel. It's as easy as that. Part A is finished.
Okay, so how do we find the angle? We need to bust out the dot product formula. Now, I know this can look a little scary, but don't worry. It's basically just a recipe. All we need are 3 ingredients. The dot product of the 2 direction vectors for the top part, and the magnitude, that's just the fancy word for length, of each vector for the bottom. Let's just knock them out one at a time.
First up, the dot product. That's the top of our fraction. We just multiply the x's, multiply the y's, multiply the z's, and add them all up. So that's 6 times 1 plus 1 times 1 plus 3 times 3, which gives us 16. Great! Numerator's done.
Okay, next ingredient, the magnitude of that first vector. This is just like a 3D version of Pythagoras' theorem. You square each part, add them together, and take the square root. So we have 36 plus 1 plus 9, which is 46. The magnitude is root 46. Check.
And we do the exact same thing for the second vector. 1 squared plus 1 squared plus 3 squared, that's 11, so its magnitude is root 11. And just like that, we have all three pieces we need for our formula.
Now, for the easy part. We just plug those three numbers back into our recipe. The cosine of our angle is 16 on top, divided by the square root of 46 times the square root of 11 on the bottom. Punch that into the calculator, take the inverse cosine, and we get our answer, about 45.3 degrees.
All right, let's move on to our last big 3D problem. And this one's a bit more involved. We're going to find the shortest distance from a point to a line. And to do that, we need a really powerful technique that involves finding something called the foot of the perpendicular.
So part A is business as usual. Find the vector equation for the line through A and B. We've got that down. But part B is the real puzzle. We have our line L, and then this other point C just hanging out in space. We need to find the one point on line L, which we'll call N, that is the absolute closest to C. And that special point N, that's our foot of the perpendicular.
So this formula looks intense, but here's what it's actually doing. It's helping us find the exact value of t for our special point N. It uses dot products to figure out how far along the line AB we have to travel from point A to be directly underneath point C. It's a projection, really. We plug in our vectors, crunch the numbers, and we find that t equals 5/11. Once we have that t value, we're golden. We just plug it back into our mainline equation to find the coordinates of N.
And there you have it. Yeah, the coordinates are a little messy with all those fractions, but that's it. That is the precise point on line L that's closest to C. I know that one was tough, so seriously, nice work sticking with it.
Whew, okay, that last one was a doozy. So, after all that heavy 3D lifting, let's switch gears. We're going to finish up with a rapid-fire drill to really cement the basics. Just some simple 2D exam questions. The goal here is just speed and making sure the stuff is second nature.
Question 1. 2 points, A and B. Give me the vector equation of the line. Go.
And here's the answer. Direction vector is b minus a, that's 3, 4. Use point A as your starting point. The equation is r equals 2, 3 plus t times 3, 4. Got it? Good.
Next one. This is even easier. You've got a point and a parallel vector. What's the equation?
This is just a giveaway. The point is, your A, the parallel vector is your D. Slap them into the formula, done. All right, last one.
Okay, last drill. Now we're going backwards. Here's the equation, and I'm telling you t equals 2. What are the coordinates?
All you do is plug in t equals 2. That gives you 2, 1 plus 2 times 3, negative 2. A little bit of math, and the point is 8, negative 3. Nice and easy.
And that's a wrap on our problem-solving session. We've covered a ton of ground today, right? From lines hitting planes to finding angles to those tricky perpendiculars. So I'll just leave you with one final question to noodle on. We know how to find a point on a line if we have t, but what if you went the other way? If I gave you the coordinates of a random point, how could you use the equation to prove if that point is on the line or not? Something to think about. Thanks so much for joining me.